Welcome to this module about probability theory. In this module, we will learn a little application of the theory that we learned in class. It's just a small application. It's going to talk about climate change, how probability theory can be tell us something about climate change. It's not our goal to prove that climate change is happening. It is quite well established, but we are not going to debate that here. But we'll just learn a small application of probability theory to climate change. And this example is taken from a book called Gamma by Julian Havel. Here is the book that I am talking about. Gamma is a number that is quite famous. It's as famous as pi, and it is quite mysterious too, has an equally great history. Um, and we are not really going to talk about Gamma, and I encourage you to read more about it. But this Gamma is approximated by a number called harmonic sum. We will talk about that. So gamma is approximated by this number called harmonic sum, and that will come up later during this talk. I must emphasize that this is an approximation. Gamma is not equal to the harmonic sum, but it is approximated by the harmonic sum. Okay, so what is the question that we are trying to tackle here? The question is to figure out how many record breaking years can we expect out of a given number of years if the probability of a given year being a record year is independent of what happens before or after. So there are two things that are important here, and one is that we are talking about averages. So this is on the average. How many record breaking years can we expect? So um, this is not like a formula. Most probability theory outcomes are more or less telling you, what you can expect on the average. And the other thing is that each year is independent of what happens in the other years. So, in other words, they are kind of random. So, it's another way of saying they are kind of random. There is a very strict definition of what random is in probability. I'm not talking about that here, but just in layman's terms, um, when you say it is independent of what happens in the other years, it means that they are random. So the first thing is that we are talking about things on the average, and the second thing is that we are assuming that what happens in any given year, um, the probability of that year being a record year is independent of what happens in the other years. And finally, what do we really mean by record year? Record year is highest of all years up to and including that year. And just for the sake of simplicity, we will assume that highest doesn't mean that um, they could be equal. So it means that they are bigger. So if a year is a record, that should be bigger than all the years that went before. So if you're talking about temperature and we want to find the record temperature, so if you say that this year the temperatures are a record, that means that it's bigger than all the years before. As I said, normally it could be equal, but just for the sake of simplicity, we will assume that it is greater than all that went before. Okay, so it's just like when you talk about record breaking in sports or politics or anything like that. So you say he scored a record number of home runs this year, means that nobody scored as many before. And it's the same thing. We look at things like temperature or rainfall, um, and see how many record years are possible. And as an exercise, you can do the same thing for your favorite things from sports or politics or movies or whatever you like. So, just as we discussed in class, you calculate the probability of an event by looking at the number of favorable possibilities and divide that by the total number of possibilities. And so, if you toss a coin 10 times, then the probability of heads is given by one half. So, it's here, and you find that by dividing the number of favorable outcomes, which is one, you only one way to get a heads when you toss a coin, and then the total number of outcomes is two. It could be heads or tails. So the probability is one half. Um, Now, as I said, the goal is to calculate the probability, or rather, the calculate the expected number of record-breaking years within a certain number of years. So, if you um, measure the temperature every year for 10 years, uh, and you look at the number of years when the temperature set a record, what is the how many years can that happen? What is the probability? And just to explain how you do that, you can try to calculate the expected number of heads that you get when you toss a coin 10 times. So the probability of getting heads in any given toss is one half, and remember the important thing is that they're independent. So because they are independent, each toss doesn't affect the outcome in the other tosses, so they're all the same probability. And in each toss, you get uh, uh, the way you add the probabilities is to say that you get one half of a head. Okay, so because it could be head or a tail. Now you will understand it better when you look at the total total number of heads that you can expect to get. So when you add the probability, you get five. So it's pretty obvious to everybody that if you toss a coin, if you toss a coin 10 times, you get five heads. And now again, this is something that's on the average. And if you toss that coin 10 times, at any given time you may get three heads. At another time you may get eight or nine or even 10. But if you do it many times, so if you toss a coin 10 times and repeat that many times, on the average you will get five. Sometimes it'll be more, sometimes it'll be less, but if you average all of them, it'll be around five. So if you uh, toss it 10 times and then 10 times again and 10 times again and do this, repeat this over and over, on the average you will get 5. Now you can toss it 100 times in one experiment, and then your probability will be I mean the expected number will be closer to 50. So when you increase the number of tosses within a certain experiment, then that also improves the chances. So basically, the more number of experiments you have, the less likely that you will get a very surprising result, like one head out of 10 or 10 heads out of 10. If you toss 100 times or 1,000 times or a million times, you'll probably get close to half the number of times as heads. It'll be close to 50 or 500 or 500,000, whatever it is. So now we can try to find the formula for the expected number of record years. So whether you're measuring temperature or rainfall or any other data you're looking at, we can try to figure out what are the how many years out of 10 or 50 or 100 you can expect there to be a record number of years. So so let's look at the probability. Now, the first year, um, it's always a record because there's nothing before it. All right. So so you'll always have one um, record year out of 10 or 100 or 50 or whatever it is. Now, the second year, it could be bigger than the first year or it could be smaller. So if it is bigger, then it is a record, right? So the probability that second year is a record is one half. So it's one out of two possibilities. And the same way, the probability in the third year is, excuse me, third year that is a record is one third. And that's again because it could the highest could happen in either the first or second or third. As I said, we are assuming that um, no two are equal. So um, then so you can keep going like that. So you have probability of a first year being a record is one, probability second year being a record is one half, third year one third, fourth year one fourth, and you keep going like that. And um, and just as you did with the tossing of a coin, when you add the probability of each toss, you get the expected number. In the same way, when you add the probability that each year is a record, you get an expected number. So this is a nice number. It's close to 3. So on the average, if you look at 10 years of history, whether it's temperature or rainfall or whatever it is you're measuring, uh, 3 of those years you can expect on the average to be record breaking years. And this kind of calculation can be done in many different situations. So, for example, if you are going to a gambling casino and you are playing dice and you play several games and each number has a certain money associated to it. So you can try to figure out what is the expected amount of money that I can get by multiplying the amount of money with the probability of getting that money and adding them up over each game. So this is a very useful formula and you can use it in many different situations. Okay, so how do we use this to discuss climate change? And the key idea is this. So if something happens randomly, just like if you toss a coin, um, the number of heads will be about 5 on the average. The same way, on the average, if you look at certain number of years, so we call it n. N is just a variable, just a name that we use to denote natural numbers. So out of n years, it could be 10 or 50 or 100. This many years will be record breaking years. So we just saw that if you add 1 plus 1 half plus 1 third up to 1 over 10, you get a 3 and approximately. And you can do the same thing regardless of what you have here, this last number. And so you can see, try to figure out if you have 10 years of records, how many of them could be, record breaking. And then if you find that there are more record breaking years than you expect, based on this formula, then you can say, um, you know, maybe there is something going on, that it's not really random. Um, as I said, when I say formula, I don't mean that it gives you the exact value that you expect, but something that you can expect on the average. So it'll be some, what the actual value could be anything, even when something is totally random, because there is always the possibility of a very unlikely thing happening. So, like I said, if you toss a coin 10 times and you're really, really lucky, you can get 10 heads or 10 tails. Um, so that's why these are random events, and that's why we talk about probability and not an exact formula. Okay, so let us calculate this number for certain values of n. So here we have, as I said in the beginning, this is approximately 3. So this is the total 1 plus 1 half plus 1 third up to 1 over 10. So here n is 10, you add the bob, you get 3. And if you do that for 50, then you get 4.549, and it's approximately 4.5. So out of 50, so if you look at conduct an experiment 50 times and find the data, then about 4 or 5 times you will get a record breaking event. And um, if you do it 100 times, then you get 5.187, so it's again close to 5. And this is close, if you do it, there's a reason why I use 135. You will see it later. So please keep these numbers in mind. So if you do it 10 times, you expect about 3, and if you do it 50 times, expect about 4.5. If you do it 100 times, expect about 5, and 100 more, about close to 150, then it's close to um, 5.5. Now you may ask, why is it growing so slowly? Um, so here it's about 3, and then it's 4.5 and 5. So between 50 and 100, there is not much happening, it's only moving by a little bit. And between 100 and 135, it's even less. So from here to here, it's about zero point 0.7. From here to here, it's 0.3 difference. And the reason is that as the numbers get bigger, the reciprocals get smaller. So here you're adding up to 1/10, and that's 0.1. Here you're adding up to 100, that's 0.01. So you're adding smaller and smaller numbers, and that's why it grows so slowly. And as I said in the beginning, this number gamma is approximated by this uh, sum, which is called the harmonic sum. So this is the harmonic sum here, this sum that we have. So it is you can use it as an approximation for gamma, and it grows very slowly, and the amazing thing is that it actually goes to infinity, even though it grows so slowly. And that's something you will learn in calculus if you haven't already done so, or you can read about it in that book. Okay, so this is the website of the National Weather Service. You can also get data about climate from the website of NASA. We will look at that later. Um, and on this website, if you go to local data and records, so you look at this here, local data and records, and you will get all these things. And then if you click on monthly precipitation, um, then you will get the um, historical data about the rainfall here in Washington D.C. So let's go there, see what happens. So I'm going to zoom it in so you can see more clearly. So this is the from the NOAA, or National Weather Service. NOAA is part of the Weather Service, and you can get more information at NASA's website. This is on weather.gov right here. So here is the annual rainfall for Washington D.C. Starting from the year 1871. So on the left side here you have the years starting with 1871, and then you can see how much we had each month. Um, this is the total amount of rainfall each month, and this is the annual total rainfall that we had, counting every drop that fell during that year, including snow and everything else. So this is the total rainfall, and so let's see what this tells us. Let's see if we can count um, the number of record years, and let's just do that for the first 10 years. So starting with 1871, this is a record because that's when the records, I mean, the history started. So just for the sake of our argument, this will be a record. So that's 38. And then the next time that's beaten is here 45.71. So I'm going to mark these in as numbers so that we can keep track of how many there are. Remember, a record is when something is higher than everything that was before. So this is one right here, and this is another record right here, and then keep going. You get three. So there's three so far, and then there's another one. This is four. So and then 60 is bigger than that. So here's one. It's five. Okay. So we got, out of the first 10 years we have five record years. So you have 38 and 45 and 47 and 52 and 60. So 60 is the record, and that happened in 1878. So that's the record so far in the first 10 years. Now let's go back to our calculation. So we said it's about 3 out of 10. So but remember, 10 is a small number. You really need bigger sample space in order to get a something closer to what is predicted. Just like if you toss a coin 10 times, sometimes you can get 10 heads. Same thing here. You had a rather wet patch apparently between 1871 and 1880, and you got 5 out of 10 years as record breaking. And but as I said, if you look at 100 years or more number of years, the expected number will match the actual number more closely. So let's see if that is the case here, and you can play with this data to look at various parts of it. Look at 10 years here, 10 years there, or 50 years here, 50 years there. So take various sections of it and see if you can count the number of record years and see how well it matches, and then see what happens on the average if you do that over many different sections. But for now, let's just look at the total number of record years. So as I said, up so far we have 5, right? So 60.09 right here is the um, record so far of the first 10 years. So this is the record so far. So keep this in mind. So we had five so far. One, two, three, four, and five. All right. So let's continue. So we'll keep going along the same. So keep your eye on this column here on the annual under the annual rainfall total, and so you can see very easily that we don't have anything bigger than 60. So right here you have another record. So in 1889 we had a lot of rain and we got 61.33. So this is number 6. So we had 6 so far. So, and then let's keep going. Let's see if what happens in the years following. You can see, again, keep your eye on this column here. You can see that it's all going to be, most of them are smaller. And as you see, when you increase the number of years, the chances of getting a record breaking year get smaller and smaller. So you see they're all, about, sometimes smaller than 40, sometimes bigger than 40, but they're around 40 for the most part. You don't get even anything bigger than 50, and much less so bigger than 60. So we are here in 1964 and we still haven't hit 60 yet. After in the beginning we saw one year with 60.09, 61.33. So we still are in the 40s and 30s. So let's keep going. And now we are in the 1960s. You can see it's it's around 40 all the time, and so we still have only 6 so far. And we'll keep going, and now we are in the 2000s, and finally we get some 60s. So in 2003 we had a very wet year, 60.83, but remember it's still not a record. Our record until now is 61.33, and then um, we are all the way up to 2014. We haven't beaten the record. So and this is the average of all of these. It's about 40, and our highest record, as we saw, happened very early, and that was 61.33 right here. So this is our all-time record. So this is our all-time record, 61.33, and that happened in um, 1889. So 61.33 happened in 1889, and that's a record. And um, the total number of record years is 6. You had one here, and then let's go up. You had 2, 3. So this is the first year. That's the record. 1, 2, 3, 4, 5, and then all the way down to 1889, 6. So we had 6 record years out of about 144, starting from 1871 to 18 2014, and um, out of them 6 record breaking. So here we are in the calculations part. This again, this is done with Mathematica program. So you can just write these formulas and it will calculate it for you. So this is the expected number of record years out of 135, and we just saw that out of so we had 6 out of 144, and the expected number of record years is 5.5 for 135 here. You can do the same thing for 144. It's not going to be much bigger than this. As we just discussed, the changes happens very, very slowly in this. So this is quite close to what we have here, what we expect. Now you may ask why we have 135 here instead of 144. You'll see that in a minute. Okay. So you already see how probability can predict, what happens in random events pretty well. Um, and it's a central law of probability that if you increase the number of experiments, the actual number gets closer and closer to the expected number. So the probability of, say, getting um, you know a 100 record-breaking years out of 144 is really really small. Even getting 50 record-breaking years out of 144 is pretty small. And if that does not happen, if on the other hand, if you get more record breaking years, then you can actually ask, is something going wrong? Now, there is no guarantee. It could, be just a miraculous coincidence, but most likely there is something going wrong. All right. So we looked at the uh, rainfall amounts for Washington D.C. from 1871 to 2014, and here we look at the um, temperature, average annual temperature in Baltimore from 1871 to 2014. Um, I made this chart using data from the same website where we just looked at the rainfall for Washington, and you can make a chart like this yourself using Excel. And so here on this axis you have the average annual temperature. On this axis you have the year in which that was measured. And so you start from 1871, go all the way to 2014. Now let's look at count the number of record-breaking years here. So here it's actually a little bit easier than the way we did it with the table for the rainfall. You just count the number of peaks that are bigger than all the peaks that were before. So basically, so if you look at the temperature from 1871, you see this is the first one is a record, just like we did in the rainfall, and then this is bigger and this is bigger. So these are all record-breaking years, and but just as in the rainfall, it gets less and less likely to find a record-breaking year as the years go on. So so from 1871 to like 1921, you have one peak here, and then so basically we are looking for the tallest peaks. So the record-breaking years um, happen um, at the tallest peaks, and we just have to count um, um, the tallest peaks until that year. So so here let's go from 1871 to 1921. So this is the first year is a record, and then this here actually we can see what the data is. So this is this data here. It's 1877 is 56.8, and then 1878 57.1, it's 1881 57.2. So this is the first year as a record, and then 1877 is a record, 1878 is a record, 1881 is a record, and then we have to go all the way to 1913 to get the next record, and then 1921 is also a record, 58.2. This is the average annual temperature. Remember, you take the temperature over every day and average it, and that's the annual average temperature. And the record was reached in 1871, 1877, 1878, 1881, 13, and 21. So you have 1, 2, 3, 4, 5, 6. So these are all the tallest peaks until that point. So this is tallest up to here, this is tallest up to here, and so on. So these are the record-breaking years. So there are 6 of them in 50. Now let's go back to our calculation. Um, Out of 50, we should expect about 4.5, and what we are getting is actually 6. But as I said, you know, things can always happen in when you're dealing with random events, and you could even get 8 out of 10. Um, uh, I mean, especially when the number is small. Over hundreds of years, you shouldn't get too many variations from the expected number. So out of 50, we had 6. And again, we can look at, let's say we start in 1972 here. And so we have 1, 2, 3, 4, and just 5. So from 1972 to 2014, so it's like 40 years, you only get 5. That's even closer to the expected number. Um, and if you look at the total out of 144 years, you have 1, 2, 3, 4, 5, 6, 7, and I'm just going to ignore this because, as I said, we are going to assume that the record means it's higher. Here it's 59.2, here also it's 59.2, although in reality it's not going to be exact. The temperature over the whole year is not going to be exactly equal for another year, most likely. So we'll just assume that we have 1, 2, 3, 4, 5, 6, 7 of them. So there are 7 out of 144. Again, it's a little bit more than what you expect. You expect really 5. Let's going back to our calculation. So out of 135, 5.5. 144 will be just a little bit more. So um, so we are getting here 7, but it's not too much. Um, Now, um, you may wonder, this is a temperature, right? Um, we know global warming is going on, climate is changing, Earth is warming up. So you may ask, what's going on in Baltimore? So you have the temperature going up to 59.2, and then the last several years it hasn't gone up. It's like 58.6 is the maximum that we have reached on the average in the last few years. And that again is another aspect of climate change, because climate change, we are studying the entire planet. All right. So we are not just looking at Baltimore or Washington. We are looking at the entire planet, and they take the average over the entire planet. Some places are getting cooler, some places are getting warmer. You might have experienced a lot of snowstorm here in DC in the last few years, and that's kind of unusual too. And they even say that that is an expected outcome of climate change, that some areas will get cooler weather because the weather patterns shift, and the air that is usually in the northern regions is meandering, wandering over to the south. That's not clear cut yet, but anyway, basically the point is that um, the local weather, you know, is not enough to decide whether climate change is going on. So, if somebody tells you, "Oh, it's cooler here, so global warming has stopped," it doesn't mean anything. So, global warming is about the temperature on the average for the entire planet. Um, so, the two things important here, that it's on the average, and secondly, it's for the entire planet. But that being said, we still see that the expected number of record years is, somewhat close to the I mean the actual number is somewhat close to the expected number, and um, as we know, in probability, sometimes it could be a little bit more, sometimes it could be a little bit less. Anyway, so this is based on the average annual temperature for Baltimore. As promised, we really want to study. If you want to understand climate change, you want to understand what's going on the entire planet, and for that we go to the NASA website to um, study the average annual temperature for the entire planet. So this is climate, a special website devoted to studying, presenting the data for climate change. All right, so we're back. Um, so this website is NASA's website, and um, so it's climate.nasa.gov. You can see it here, and you have all kinds of information here. You have the um, global temperature, which we are looking at, and then you have the carbon dioxide. You can click on each one to get the information for that. So um, it'll show you how much carbon dioxide has been increasing, um, and you can see here the Arctic ice, how that has been changing over the years, and you can uh, play this video to see over the years an animation of how the ice has been changing. Now, going back to temperature, um, so you see here the global annual temperature, land or averaged over land and ocean, from 1880 to 2014. So um, now this says temperature anomaly here, and it's not the actual temperature, but the difference from a certain reference. But it's not um, that different from the actual temperature. The actual temperature itself, each place has such a varying temperature. So if you take the average, it won't tell you that much. So what they do is for each place they measure the anomaly or the departure from the reference point, and then they average the anomalies for all of the places on Earth. They divide the Earth into small portions and take the average for each, and then take the average for all of those small portions over the whole Earth. And on the video here will show you how it's been changing. You see the blue, the more the red and the yellow, so on this scale the more the difference, and the difference is just 1 degree Celsius, which is about 2 degree Fahrenheit. The total difference from here to here is about 1 degree Celsius, and if it gets close to 2, it will become very red. So this is the difference for various parts of the Earth, starting from 1884 going to 2014. As you can see, as we get closer to 2014, there is more yellow and red. That means that more places are getting warmer than normal, than the reference point. The reference point is at 0 here, and that's the average temperature over the whole 100-year period. And that's just one fixed temperature. And this shows how the actual temperatures are varying, are getting bigger than the reference temperature. Anyway, so that's all just the background, and for us, the important thing is to see how to count the number of record-breaking years. Now, um, again, you must remember that these numbers can always vary. Probability doesn't give you the exact value. Um, Sometimes it could be more, sometimes it could be less. But if you take the number of record years over a long period of time, say like 100 or 1,000, the expected number should be close to the actual what is happening. So if the actual number is much more than the expected number, then you know that most likely that something is going on that is not really random. So let's look at the record breaking years here. I'm just going to actually let me show you a better picture where you can easily count the number of record breaking years. So this is the same graph that we just saw, and it's just so it's the same graph as you have on the left here, and but it's easier to count the number of record breaking years. This red line in the middle is the 5-year rolling average. So every year they calculate the average for the preceding 5 years, and that's the red line. These black dots are the annual averages over the entire Earth, and the total change is about from minus zero point 0.4 to zero point 0.6, so about 1 degree Celsius or about 2 degree Fahrenheit. That's how much the Earth has warmed in the last 140 years or so. So let's count the number of record breaking years. The first year is always a record right here, and then this is the tallest peak after that. So number 2, this is the next tallest peak, number 3, number 4, number 5, and number 6, number 7. I'm not going to count that ones that are equal, as I mentioned. There's a number. Okay, let me go back. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So you see, we have like 17 record breaking years just out of 143. And especially towards the end, you see that there is a lot of years where the temperature is bigger than all the years before that. And that's what they mean when they say, when you look over here, it says 9 of the 10 warmest years on record have occurred since 2000. And in fact 2014 was a record where it was the warmest that the average annual temperature on the earth has ever been in known history, in recorded history. These temperature records were kept starting 1880s, and in all of that recorded history, last year was the warmest in terms of the average annual temperature over land and ocean combined. And so that shows you, um, that maybe there is something that is more, something happening, something wrong going on, that maybe it's not really random. Um, but as I said, our goal is not to prove that climate change is going on. Our goal is just to give an example, and I hope that you got a better idea of how you use probability in real life. And you can use probability in many places, not just when you talk about climate. You can do it um, on um, sports. You can do it for politics, and many other areas. In fact, there is an entire website devoted to, using probability theory, called 538.com. Many of you probably already have heard of it. So this is the website 538.com. If you follow the elections, you remember that um, Silver, producer of this website, he um, predicted the election results pretty well, and he really uses mostly statistics and probability theory. And so the website is 538.com and talks about all kinds of things: politics, economics, science, wildlife, sports. So it's a good website if you want to learn more about the application of statistics and probability in real life. So back to our presentation. So um, this is um, you know how you use probability to check whether what the number of record years that you can expect, whether that is what you expect or is it too out of ordinary. And to finish with, let me give you some exercises that you can work on. I already talked about some of them. You can try to play with probability or do some experiments by tossing a coin or throwing a die, and you know um, repeat the experiment several times, or do the same experiment with more number of events. Like you can toss a coin for 10 times and you know do it several times, or you can toss a coin just once for 100 times. And so there are a lot of things you can do, play with. And um, you can also just like we did, you can look at historical charts of various data, whether it's climate related or sports related or politics related or any other subject that interests you. Um, and we looked at the temperature for Baltimore and the rainfall for Washington, D.C. This area has been on the cooler side lately, but you can definitely find other cities, probably on the west coast, where it's been warmer lately. So these are some experiments and exercises that you can do on your own, and you should try them and learn more and come up with some answers and submit them in class. So with that, I'm going to stop this